Okay, the Gram-Schmidt process, just have to keep on adjusting that screen. The Gram-Schmidt process is ultimately the goal here is to find one, an orthogonal basis for a vector space, but then to take that orthogonal basis and also transform it into an orthonormal basis, where one, the vectors all together are said to be orthogonal or perpendicular, but then after that you want to scale them down and make the vectors not just orthogonal but also orthonormal. That simply means that they are perpendicular and also each vector measures one. Its norm length is one. Gram-Schmidt process is a very classic method to finding this orthogonal or orthonormal basis or orthogonal or orthonormal set. Here, definition: a set of two or more vectors in a real inner product space is said to be orthogonal if all pairs of the distinct vectors in that particular set said to be orthogonal, and an orthogonal set with each vector that has norm length of 1 is orthonormal. What I'm going to do is talk about the theorem and then give the projection theorem and then try to illustrate it so that you understand in the second theorem here how is U produced. So first, if S is a set of vectors that are orthogonal in some orthogonal set of non-zero vectors in an inner product space, then we say that S is also linearly independent. One neat way to get linearly independence is that the vectors would be orthogonal. So here, S being this orthogonal basis for some inner product space V, and if U is any vector in V, then U can be written, watch this, as a linear combination of the vectors from S. The linear combination of the vectors would be V1, V2, and so on to Vn, times some constant, or that scalar. I don't know if you recall from when we were talking about a vector some vector U that if a space is a vector space or even a subspace, then any vector in that particular space can be written as a linear combination of the bases. Do you remember that? The whole idea of a space or a set of vectors that are said to span a vector space. I can take any vector in a vector space and write that vector, this vector that I'm taking is U. I can write U as a linear combination of the given vectors from the basis. So here S is said to be a basis. So if I take some vector U, let's say that here U is some vector in the vector space, and so I have this vector U, and also in the vector space I have the basis for V, which is V1, V2, V3, V4, and so on to V sub n. So I can write U as a linear combination of these given vectors in the vector space. Now, what I have here, we said, is some K sub 1 times V sub 1 plus K sub 2 times V sub 2 plus, and so on, plus K sub n times V sub n. we can write U as a linear combination of the given bases. Now the question is, can you find those constants, those scalars, K1, K2, and so on to K sub n? Do you know what their best approximation happens to be? This inner product divided by that norm squared, plus and so on. K sub 1 is this guy. K sub 2 is, that's his best form. The best form of a seed is a plant or a flower. The best form of a baby is a grown man. The best form for water is wine. Lord turned water to wine. He never changed the chemical composition of anything. You know, person was lame, he made them well. They couldn't see, he gave them sight. Right? If they were dead, he made them live again. That's the best form. He took water, and water, if it sits up long enough, it wants to be wine. So the best form for K1, K2, and so on to K sub n is this complicated scalar, this inner product of U with V sub 1 divided by the norm of V sub 1 squared, and then and so on. Now the question today is a strong question, is how do we get those guys? I want to raise that question. Now the author does not raise that, but I do, because it's important in linear algebra. Everything else is just a formula. The Gram-Schmidt process is just a formula, just plug the information in. But my thing is, with that formula, it involves these guys. And so to me, it's always good to know, where does this come from? Why is that important? Because if I forget this formula, the image of where it comes from, and I'm going to draw it out for you, you can always produce this. That's important. So here, this K sub 1 is this inner product of U with V sub 1 all over the norm of V sub 1 squared. K sub 2 is the inner product of U with V sub 2 over the norm of V sub 2 squared. K sub n is the inner product of U with V sub n all over the norm of V sub n squared. Okay. So we'll come back to this here. Part B, well, Part A says that if S is a basis, and it happens to be an orthogonal basis for some inner product space V, then U can be written as a linear combination of those vectors from the basis with the scalars K1, K2, and so on, K sub n, being that number there. Now look, again, this inner product divided by this norm squared is a number, so it's a scalar. If S is orthonormal, that means that if it's orthonormal, that means that it's orthogonal, but also each vector, V1, V2, and so on to V sub n, their norm is equal to 1. So that denominator, so the norm of V sub 1 is going to be 1 squared. It's just 1 downstairs. So that's where that goes. Because here, S is now said to be orthonormal, that each vector, V1, V2, and so on to V sub n, their norm length is equal to 1. So here you're just dividing by 1. So it's the same formula, but each norm is equal to 1. Now, very classic theorem in mathematics, the so-called projection theorem. I will illustrate this for you, that if W is a finite dimensional subspace of an inner product space V, then any vector U in V can be expressed in exactly one way. Here, that U, any vector U, is said to be the sum of its parts, two parts. The first term is said to be its projection on the plane, and the second, that's W sub 1, and then W sub 2 is said to be its perpendicular or its orthogonal complement. U is equal to W sub 1 plus W sub 2. It says U is equal to W sub 1 plus W sub 2. This plus is a strong plus. We call it a direct sum. So in any other textbook, you will see the plus sign with a circle around it. So it's not the typical arithmetic plus sign that we're accustomed to seeing. It's saying something. But what is it saying? Well, this is saying that U, just in a nutshell, if you're in physics, U is said to be the resultant vector that spits out in space. That resultant vector is said to be composed from a triangle where you have the base leg and you have the altitude. Right? So W sub 1 is the base side and W sub 2 is at altitude. And U is the resultant. That's what they're saying. Let's see if I can illustrate it here. So it says, see, W sub 1 is in W, and W sub 2 is in the perpendicular or the orthogonal complement of W. Let's see if I can draw it out here. So here I have this plane. This is a subspace, W. And here, this is U. That's the resultant. And this is said to be W1. This is W2. W2, obviously, is in the orthogonal complement of W, right? It's perpendicular, right, to W. So there could be some angle. Here we won't deal with the angle because we're going to keep everything algebraically by only focusing on the vectors. Yes, sir.
Say that triangle you got there was a square. That means you have two W sub 2's. So would W sub 2 be the sum of those two?
U is always the resultant. If it's a square, then U is the diagonal. Right? Yes, sir. Now, this, notice that W sub 2 is equal to U minus W sub 1. And to be honest with you, to be able to get the projection theorem, that W sub 1, the way they have it written here, is not so. W sub 1 is actually short. It's a short vector. It's on that same line, but it's shorter. To produce W sub 1, or to produce that entire length, we have to multiply by some scalar, some number C times W sub 1 to get that whole base side. So the projection of U onto W is written as the projection of U onto W, and it's equal to the inner product of U with W sub 1 divided by the norm of W sub 1 squared times W sub 1. That's fine. That's the projection theorem. Have you seen that before? If you've had calculus 2, you saw it in calculus 2. Well, now understand that this information is really what this theorem up here is trying to say in terms of what U is equal to. Right? Some inner product divided by some norm squared times that vector. Right? Same idea here. Now to produce this, because this is really the crux of even the Gram-Schmidt process once we see it. So to produce this result, let the projection of U equal to some scalar C times W sub 1. So what we're saying here is this. W sub 1 is just that. C times W sub 1 becomes the entire length. So here, now, if that be the case, then C times W sub 1 dot product with W sub 2 is equal to 0. Because W sub 1 and W sub 2 are perpendicular, so the dot product is equal to 0, right? Two vectors that are orthogonal, their inner product is 0. You know, that's the same thing as saying C times W sub 1 comma W sub 2. That's the inner product, same thing. Since orthogonal vectors dot product is 0. Now also, we have U here, which is set to equal to this W sub 1 plus W sub 2, and I'm saying that this W sub 1 is actually C times W sub 1 plus W sub 2. This implies then that W sub 2 is equal to U minus C times W sub 1. The Gram-Schmidt process will ask us to find an orthogonal basis. An orthogonal basis is also orthonormal. And in order to get the orthogonal basis, that is, I don't want vectors in W, I want vectors in W perp. To get the vectors in W perp, they will look like U minus W sub 1. Basically, I'm looking for all vectors that are parallel to W sub 2, which is going to be that vector U minus something else. That's important because you'll see it and you'll say, where does that come from? It comes from this U minus CW sub 1 is putting me upstairs that the vectors are standing up, right? W sub 2 and everything that looks like W sub 2. I'm looking for those vectors that are standing up. Here I have some basis on the floor, but I want to find these perpendicular vectors, these lines that stand up that's perpendicular to the plane. And so it's going to always be some U minus some vector. Now here, this is a period. And so what I have is, I'm going to go back here, take C times W sub 1 dot product with W sub 2 is equal to 0. I just went back here. that is perpendicular vectors, their dot product is 0. That's all I've said. Now I'm going to replace the W sub 2 with U minus C times W sub 1. This implies that C times W sub 1 dot product with U minus C times W sub 1 is equal to 0. Now simplify that. That implies here that C times W sub 1 dot product with U minus C squared times W sub 1 dot product with itself is equal to 0. Okay? So here, if I factor out a C is some scalar that's not 0. Well, it can't be 0 because if W sub 1 is this little vector right there, then C times it extends it. Right? It stretches W sub 1. So C is some number. So I divide through by C, and this implies that I have the dot product of W sub 1 with U minus C, the dot product of W sub 1 with itself is equal to 0. This implies that we have C times W sub 1 dot product with W sub 1 is equal to W sub 1 dot product with U. Right? Just added C times the dot product of W sub 1 with W sub 1 to both sides. Now the dot product of W sub 1 and W sub 1 in terms of a norm, I can write that as what? The inner product of the same vector with itself is equal to what in terms of a norm notation? No. Okay, the inner product of a vector with itself is the same thing as the norm of the vector in what? Yes, the norm, right? The norm of the vector squared. Perfect. So here, this is C times the norm of W sub 1 squared is equal to the inner product of U. Remember that the inner product is commutative. So here, this is the same thing as U dot product with W sub 1. This implies that C is equal to the inner product of U with W sub 1 all over the norm of W sub 1 squared. So C here is the constant. It's that coefficient, that K sub 1. So, but we said that what we're looking for is this projection. Let the projection of U. The projection of U is this image. The projection. I got U as this resultant vector up in space, but if I project U onto the plane surface, right, we're calling that C times this W sub 1. Right? Basically, the projection of U onto the surface is just a shadow on the ground. Right? That's equal to, look here. So we say here, this projection of U onto W is equal to, we said C times U. Or C times, W sub 1. We said it right there. The projection of U is C times W sub 1. But C is equal to this. So this is the inner product of U with W sub 1 all over the norm of W sub 1 squared times W sub 1. Now, what's in W? What's in W is V sub 1, V sub 2, right, V sub 3. Remember that here, this W is no more, capital W this is a subspace, right, of V. So W is in V as well. So that is to say, the projection of U onto W is equal to the inner product of U with V sub 1 all over the norm of V sub 1. Remember, these vector V sub 1s, V sub 2s, whatever, they are in W. So I want to show you that this funny scalar times the vector is no more than this number C, which we get to be the inner product divided by the norm squared. So now you know where it comes from. Right? That's the so-called projection theorem. So this theorem, let W be a finite dimensional subspace in an inner product space V. If that be the case, then if these vectors, V sub 1 to V sub n, forms an orthogonal basis for W, and U is any vector in V, then the projection of U onto W is just what we just got through showing. We just showed it for just one term, but that's the summation of all of them, and it's just the same recursive process. If V is orthonormal, then your denominator is 1. Now, a very simple theorem, but it says a whole lot. Every non-zero finite dimensional inner product space has an orthonormal basis, and the Gram-Schmidt process goes after the answer to find it. So if you have a non-zero finite dimensional inner product space, then within it, it is said by this theorem, it has to exist some orthonormal basis, at least one. Well, how does it look like? Well, the Gram-Schmidt process gives us that. Gram, by the way, he was a student of Hilbert, one of the giants in study of mathematics. If you looked at my notations back for 6.1, I made some statements in terms of the Hilbert space and the Banach space and the metric space. And so Schmidt, who was a mathematician and somewhere else, around about the same time, gave solutions to this process. Basically, they were both trying to prove the theorem for their dissertation. And Gram, I believe, got it before Schmidt. Schmidt was using it for auxiliary science and statistics with the insurance companies. Back then, they didn't have these supercomputers, so everything was by hand. And so he was able to produce pivotal points for the accumulating interest in certain types of investment by using this process. So here, the objective to convert any basis, U sub 1 to U sub n, into an orthogonal basis, and then from there, convert the orthogonal basis to an orthonormal basis. We first try to convert the basis to an orthogonal basis. U1, U2, and U sub n is what's given. You need to find V1 and so on. So let V1, the first V1, let it be the first vector in U sub 1. That's fine. And then from U sub 1, you start the turning to find the next vector that's said to be orthogonal. Remember I told you that the orthogonal vector is always going to be that U minus that W sub 1. I'm looking for W sub 2. So here this is U minus, basically this right here is W sub 1. So I'm looking for those orthogonal vectors. And you see the process, you see the number nomenclature there as that goes through. So v sub 2 is u sub 2 minus the inner product of u sub 2 with v sub 1 divided by the norm of v sub 1 squared times v sub 1. V sub 3 is u sub 3 minus the inner product of u sub 3 v sub 1 divided by the norm of v sub 1 squared times v sub 1 minus the inner product of u sub 3 and v sub 2 divided by the norm of v sub 2 squared times v sub 2. Right. And step 4, I'm only going to give you U1, U2, and U3, so you don't have to worry about anything beyond step number 3. You see how long that process would be if it's in steps. The neat thing about computer programming is that you figure out the summation for 1, and then you let as n goes to 1 to k or whatever it may be. To the question of finding an orthonormal set, take each v1 to v sub n found from above and divide each vector by its associated norm to produce the orthonormal set. Now let's look at this problem here. So the first thing we do is let v sub 1 equal to u sub 1, so that's 1, 0, 0. And then, secondly, let v sub 2, which we're looking for, is equal to u sub 2 minus the inner product of u sub 2 with v sub 1 all over the norm of v sub 1 squared times v sub 1. So this is u sub 2, which is 3, 7, negative 2, minus the inner product of u sub 2 with v sub 1, and that's 1, 0, 0, all over the norm of v sub 1 squared. Well, the norm of v sub 1 squared is just 1 squared plus 0 squared plus 0 squared. That's just 1. So this is 1, and then this is times v sub 1, which is 1, comma, 0, comma, 0. So we simplify that. V sub 2 is the 3, 7, negative 2, minus the inner product up here is just 3 divided by 1, so that's just 3 times the vector 1, comma, 0, comma, 0. So we simplify that. This is 3, 7, negative 2 minus 3, 0, 0. So it just gives us 0, 7, negative 2. That's v sub 2. Now let's find v sub 3. V sub 3 is a little bit more. V sub 3 takes u sub 3 and says now this is minus the inner product of u sub 3 and v sub 1 all over the norm of v sub 1 squared times v sub 1 minus the inner product of u sub 3 with v sub 2 divided by the norm of v sub 2 squared times v sub 2. So the u sub 3? Yes, sir.
That only hits the very front. We never have a use of 3 in front of the next part of it.
No, it's just 1. Exactly. Yep. Because once you do that minus there one time, then that's going to always throw you in the perpendicular plane. So here, v sub 3 is u sub 3, which is 0, 4, 1, minus the inner product of u sub 3, 0, 4, 1, dot product with, put my dot there, with v sub 1. V sub 1 was that 1, 0, 0. And that was all over the norm of v sub 1 squared. And that was times v sub 1, 1, comma, 0, 0. Then this is minus the dot product of u sub 3, which is 0, 4, 1. Dot product with v sub 2, we just found that one, 0, 7, negative 2. And that's all over the norm of v sub 2 to be squared, 0, 7, negative 2, to be squared times v sub 2. So now we simplify this. 0, 4, 1, minus. You do the dot product here, just get 0, right? Now, it doesn't happen. You don't make a church out of that, but it's just for this problem we get 0, right? You know what I mean? Don't make a church out of it. You know, some people, they'll read a certain passage, they'll stop right there and we're going to make a church right here, you know. And then some folk over there, they'll go and read a passage, we'll make a church out of this, you know. Adrian Rogers said that when the Lord was healing people of blindness, you know, he used different methods each time. You don't put a claim on one to say, okay, if you want to get healed, you know, from blindness, somebody got to spit on you, you know, or somebody got to spit in the ground and make a clay, or somebody's got to, you know, just touch you and you'll be able to see. So Dr. Rogers said, you know, you don't want to make a church out of that, because you got some folk over here, they'll say, okay, this church is going to be called Touchite Baptist Church. Church over here is going to be called Spitite Baptist Church. This church over here is going to be called Mud Soaking Baptist Church, whatever. So just because if I get a 0 for a particular term, it's just because of those numbers. It's not the process. You know. So here, this is the dot product. This is 0 plus 0 plus 0, that's just 0 divided by 1 times a vector, that's just 0. Minus the dot product over here as 0, 28 minus 2 is 26, all over. You take that norm here of 0, 7, and negative 2, so that's going to be 0 plus 49 plus 4, so that's the square root of 53 squared, it's just 53 times 0, 7, the vector 0, 7, and negative 2, right? So we're squaring that, so it's just 53 there by itself. So this is 0, 4, 1. This is minus 26 over 53 times 0, 0. 26 times 7. $182 over 53, and then negative 52 over 53. So V sub 3 is 0 minus 0 is there. 4 minus 182 over 53. This is 30 over 53. And then 1 plus 52 over 53 is 105 over 53. Okay. So now I have 3 orthogonal vectors. What are they? Let's see. The 3 orthogonal vectors would be 1 v sub 1, that's what it has become, We claim that first one to be so. And then v sub 2, we found it to be here. And then v sub 3. So now the Gram-Schmidt process says to convert the orthogonal vectors to orthonormal. We take each vector, we divide it by its norm. That's how we get the unit vector. So it becomes not just orthogonal, but also orthonormal. So here what we have is, let Q1, Q2, and Q3 be the orthonormal vectors. So Q1 is equal to V1 divided by the norm of V1. Q2 is equal to V2 divided by the norm of V sub 2. And Q sub 3 is equal to V sub 3 divided by the norm of V sub 3. So, let's see here. V sub 1 was 1, 0, 0. I think that's right. Yes. What happened to my notation? So this is V sub 1. The norm of V sub 1 is the square root of 1 plus 0 plus 0. We just get 1. So Q sub 1 is equal to 1 comma 0 comma 0 divided by 1, and this is just 1 comma 0 comma 0. Now V sub 2 was 0, 7, negative 2. I think that's right. 0, 7, and negative 2. Its norm is the square root of 49 plus 4. We get the square root of 53. So Q sub 2 is V sub 2 divided by its norm, 0, comma 7, comma negative 2 over the square root of 53. So this is 0, comma 7 over the square root of 53, comma negative 2 over the square root of 53. Now for for Q sub 3, we need V sub 3, and we found that to be 0, is it 30 over? Pardon me? To rationalize which one? It's already rationalized. Right? If you take the norm of Q sub 2, you'll get 1. Are you saying you want to rationalize to say 0, comma 7 times the square root of 53 divided by 53? Oh, you're talking about that. No, that's fine. You can do that, or you can leave it like how I have it. It doesn't matter. Yeah. Sorry about that. Yeah. You were talking about the simplification, so. Yeah, no, that's fine. You know, back in earlier math, you got teachers that say it has to be simplified. Like, I was never that jerk. You know, you had some teachers like that, man. You got to write it in this form, and if not, it's wrong. It's still the same thing. You know, as long as it's simplified in smallest terms. Like, you wouldn't say 5 over 10, you would say 1/2. You know, I understand take off a point because they didn't simplify that, but the rationalization of something like that, yeah, we're not saying that. He's not saying the rounded either, because the rounded would not be exact. You're exactly right. The radical is exact, but he's saying, do you get rid of the radical downstairs? You know, and my thing is just leave it the way it is. So this was. So V sub 3, go back up here, that's it there. And then 105 over 53. So we got to find its norm. So it's going to be the square root of 30 over 53 squared plus 105 over 53 squared. Pardon me? To square the radical? There's no square over here. If there's a square there, then there's no radical. Yeah, it's squared inside. Pardon me? 7 squared is 49. I can do that because that's easy, right? These numbers over here are too big for me, man. I hadn't had my frog legs yet. So we used the calculator. We think I'm Einstein, man. I'm this country dude from South Alabama, man, having a good time. So we use a calculator. 15 times the square root of 53 all over 53. My graphic calculator just gave me that directly. Huh? Yep. So we need what? Q sub 3. That's going to be V sub 3 divided by the norm of V sub 3. So V sub 3 is the 0, 30 over 53, 105 over 53. That's divided by 15 times the square root of 53 over 53. So this is 0 there. The 53 goes upstairs, divided, it counts out with that 53. This is 30 divided by 15. So I get here 2 all over that square root of 53. And then the 53 and that 53 would cancel out. 105 divided by 15 is, looks like that's 7. So this is 7 divided by that square root of 53. And so what you're looking for in terms of the orthonormal basis would be these guys right here. Now, there's one problem left. My time is coming to an end, and so let me just give you the answers to this one, and then you can work that out and see if your answers match what I have. So first you're going to find V1, V2, and V3. So V1 is 0, 1, 2. V2, excuse me, is negative 1, negative 2 over 5, and 1/5. And V3 is 0, 0, 0. So Q1 is 0, 1 over the square root of 5, 2 over the square root of 5. Q sub 2 is negative 5 over the square root of 30, negative 2 over the square root of 30, and then 1 over the square root of 30. Yep. and there's no Q sub 3 for that one, and that uh, could mark for good discussion in terms of what happened to Q sub 3. Q sub 3 did not form because V sub 3 is the zero vector. Okay? So then the question would be, with those two vectors, V1, V2, do they form on an orthogonal basis? And then does Q1 and Q2 form a orthonormal basis? And it's funny how that question is raised. Do they form orthogonal and orthonormal basis for the vector space? No. But do they form an orthogonal or orthonormal basis for the subspace spanned by U1, U2, and U3? Yes, they do. Because U1, U2, and U3 become degenerate because once you break those down and looking for the so-called orthogonal basis, V sub 3 goes out to be the so-called zero vector. And so, but for its particular space, vectors that look like it, you can use Q1 and Q2 to produce them, right? But Q1 and Q2 cannot produce all the vectors in R3, right? Only for that particular subspace, not for the overarching vector space. Let me close this out, then just make a couple of comments on the exam.